Okay, so you might look at calculus and just see another math class, right? But what if I told you it's actually your secret weapon for all your science courses? It's the toolkit scientists use to model pretty much everything in the real world, from how a virus spreads to how fast a chemical reaction happens. So let's open it up and see what's inside. I mean, think about it. The world around us is always in motion. Populations are growing, chemicals are reacting, things are constantly changing. So the big question is, how do we capture all of that movement and turn it into something we can actually measure and, even predict? Whether you're in biology class tracking how a virus takes over, or you're in the chemistry lab measuring reaction speeds, at their core, both of these fields are really about one thing: studying the nature of change. And the language that was literally invented to describe and predict all this change? Well, that's calculus. It's kind of like the universal translator that connects the, let's say, chaos of the natural world to the clean, ordered world of mathematics. All right, first tool out of the box, the derivative. What's it for? It's all about pinpointing a single, precise, instantaneous rate of change. So in the simplest terms, a derivative answers the question, how fast is this changing right now? Not over the last hour, not in the next minute, but at this exact instant. It's like a snapshot of speed. Okay, let's make this super real. You've probably seen a graph like this in your immunology chapter, right? It's showing antibody production. Now, if we ask how fast are antibodies being produced on exactly day 10, well, that is a classic job for the derivative. It's nothing more than the slope, the steepness of the curve at that one single point. But we can go even deeper. The first derivative tells you the speed. Is the antibody count going up or down? But the second derivative, that tells you about the acceleration. Is the production speeding up or is it starting to slow down? That's what tells us how the curve actually bends, what we call its concavity. And trust me, you are going to see this concept everywhere. When you're calculating the half-life of a chemical or modeling how a population decays, what you're really doing is using derivatives of exponential and logarithmic functions. Those functions, based on e and the natural log, are the absolute bedrock of modeling natural processes. So let's move on to our next tool, which kind of builds on the last one. If derivatives are all about one single instant, then integrals are about looking at the entire journey. Exactly. While a derivative takes a snapshot, an integral does the total opposite. It adds up all those little moments over a whole period to give you a grand total. And visually, it's just the area under the curve. Let's go right back to that same immunology graph, but we're going to ask a totally different question this time. We don't care about the rate on one specific day. We want to know the total amount of antibodies produced between day 7 and day 21. For that, we need an integral to find the total area under that section of the curve. See the difference? This whole idea of accumulation is huge, and it shows up all over your exams. Need to find the total distance a particle traveled in physics? Integral. Measuring cardiac output by tracking the total amount of dye that passed through the heart? That's an integral too. It's all about summing things up over time.
And now for the final tool in our kit. This is where everything, derivatives, integrals, all comes together. We're talking about differential equations, and they are how we build powerful, predictive models of reality.
So what in the world is a differential equation? It's actually simpler than it sounds. It's just an equation, a rule, that connects how fast something is changing to how much of it there is. Think about it. The more a virus spreads in a population, the faster the number of infected people grows. A differential equation is how you write that rule down mathematically.
And this is exactly how scientists build models. First, you observe a system, say how medication breaks down in the blood. Then, you write a differential equation describing that rate of change. You solve that equation, and boom, suddenly you have this incredible tool to predict what's going to happen next.
Okay, I know you've seen problems like this in your physics textbook. When you're solving this, you're not just doing some random math problem. You're actually analyzing a differential equation that models a real-world system, in this case, an RLC electrical circuit. It all connects. So, these first-order equations are perfect for things like exponential decay, like how medicine levels drop in your blood. But for stuff that goes back and forth, stuff that oscillates, like a swinging pendulum or a vibrating electrical circuit, for that, you need the power of second-order equations. So, what's the big takeaway from all this? You've got these amazing tools in your hands, but how do you go from just knowing about them to actually mastering them for your exams? I want you to think about it like this. The baccalaureate exam isn't looking for bricklayers, people who just memorize one fact after another. It's looking for architects. It wants to see that you understand the blueprint, the calculus, that holds all your science subjects together in one big, beautiful structure. And how do you become an architect? Well, there's no secret. It's practice. The problem sections in your math manual, those are your construction sites, where you get your hands dirty, where you apply these tools to all sorts of real-world situations, and where you really learn to see the bigger picture. So look, you have the blueprint and you have the tools. You can literally model a heartbeat, a chemical reaction, a growing population. The only real question left is, what part of the world are you going to build a model for first?